There is a very specific story we tell ourselves about how software gets made. We write down what we want, hand it to a programmer, and they translate those instructions into code. This linear approach feels rational because it treats coding like language translation. We assume that if the initial instructions are precise, the final product exactly matches the blueprint. But digital rules are fluid. The moment a program executes, it stops being static. In practice, development is a continuous cycle where intentions are modeled, deployed, and observed to see how they behave. The challenge of engineering isn't found in the act of translation, but in the behavior those instructions trigger once they are set in motion. To see that behavior in action, we can start with a minimalist rule set. Here is a document with exactly 3 rules. A follows B, B creates C, C changes A. Executing these rules on simple boxes, they interact and branch into 2 possible states. These compound, rapidly multiplying into 8, then 64 variations. Looping again, they expand into over 4,000. The chaotic pattern hits the screen's edges, escaping our ability to visualize it. The description of a system can fit on a single page, but the system it creates instantly grows larger than the biological capacity of the human brain to map it. Faced with a system they can no longer hold in their heads, an engineer's first instinct is to try and regain control by mapping every single interaction. This is exhaustive modeling. You document every possible state and every variable, hoping to freeze the environment in a giant schematic. But as the system scales, those maps collapse. The interconnecting lines overlap until the information becomes an unreadable, solid block of noise. When a system's complexity is practically infinite, attempting to model everything leads to a total loss of comprehension. If mapping fails, the secondary defense is testing. We secure the system by running trials to prove that specific, isolated pathways function correctly. Visualize the software's total state space as a dark void. When we run tests, thousands of points light up to confirm they work. But as we pull back, the ratio changes. The successful tests become microscopic specks, swallowed by unexplored possibilities. Tests sample a system. They do not contain it. Mathematically, a total biological understanding of the system is impossible. If total comprehension is impossible, we're left with a paradox. How does complex software successfully run the modern world? The answer is cognitive compression. Engineers intentionally ignore the infinite noise to focus on a few structural anchors: the boundaries, the invariants, and the failure modes. By identifying the absolute minimum number of constraints required to keep the system predictable, an engineer can navigate the chaos. These constraints form a mental model, a human-scale proxy that replaces the infinite reality of the software. A software engineer manages these cognitive limits every day. They function as a cognitive bridge, constantly updating their simplified model as the actual system reveals new, jagged data. The role is to maintain a tractable theory of an intractably complex system. This principle applies far beyond software. Good architecture maximizes how much behavior can be understood from the absolute fewest number of concepts.